So let's imagine a potential that looks like this. So V is, this is, say, V naught, and this is 0. And the potential goes on at x equals 2x equals infinity, and x equals minus infinity with this value, V naught. But at say t equals 0, we have a wave function, which is some c times x for, well, let's say that this is L over 2 and this is minus L over 2. So let's say for that range, this is the wave function, and 0 outside that range. And we want the probability of finding the particle between, let's say, minus L over 4 and L over 4. So in this region here. So at t equals 0. So we need to normalize this, figure out what the c coefficient is. So we have a c modulus squared, x squared, that's psi x0 modulus squared. And we want to integrate that over the entire space from minus infinity to plus infinity, but the function is only non-zero in this range, so that determines our limits of integration. We have to integrate this, and this has to give us 1. So we get c modulus squared. We get a factor of 3, right? It's x cubed over 3. So we're going from minus L over 2 to L over 2, and this gives us, we have the 2 over 8, right? So 2 times 2 times 2 is 8. So we have 2 of those. So we have 2/8 coming from here. So we end up with c modulus squared over 3 times 2L cubed over 8. And that gives us c modulus squared. This is 4, so this becomes 12L cubed, and this has to equal to 1. So we have that the modulus of c is the square root of 12 over L cubed. So now we can figure out the probability of finding the particle between minus L over 4 and L over 4. And so it's 12 over L cubed x squared. All right, that's psi modulus squared. We're going to integrate that. It's the same integral, so 12 over L cubed times the same quantity we had before, x cubed over 3, but evaluated from minus L over 4 to L over 4. And this gives us, right here we have a 4. Of course, the L's will cancel because we need a pure number, so we know we'll get an L cubed from here. We can see that. We have 4, that's what we're cubing, and so we get 2 factors of 1 over 64, and this ends up, the L cubed, of course, and that gives us 1/8. So the probability of finding it in this region here, between here and here, is 1/8. We could have estimated that, right? The probability goes like x squared, and so it's smaller in this region, it's greater further away. So let's now estimate or determine the probability that we'll find that if we make a measurement of energy, we'll get the ground state. So E1 is the ground state. What is the chance that we're going to get the ground state? What's the chance that we get not the first excited state, but the next excited state, and so on? And the answer is 0, because this function is odd, right? We have a symmetric potential, and the solution that we have here, psi of x and 0, is an odd function, and so we'll never get any coefficient that is, so for n equals odd, these are even functions, right? This is going to be psi n star of x times psi of x 0 in dx, and these are all even functions, and so because this is an odd function, it's an overall odd integral, and of course we're going to be going from minus we're going from well, yes, it's valid only in this range here, so from here to there, but it doesn't matter, because as long as we are symmetric, we go from minus x naught to x naught, these coefficients must vanish.